General relativity gives us a smooth, continuous Riemannian manifold. Quantum field theory gives us a vacuum defined by violent, discrete fluctuations. When physicists attempt to calculate the energy of the vacuum using both frameworks, the math produces a 120 order of magnitude discrepancy. Unified dynamics targets the root of this failure in our starting assumptions. The models clash because we have treated spacetime as a fundamental continuous manifold and gravity as a primary force. Instead of a fabric, the unified dynamics framework starts with a discrete mathematical graph, the K4 tetrahedron. This seed is driven by an iterated function system, recursively scaling and multiplying to generate a dense Sierpinski fractal lattice. To solve quantum gravity, we must discard the concept of a fundamental metric. We have to examine reality as the structural output of this discrete combinatorial packet network. As we examine this network at scale, the fractal lattice contracts by 4 to the negative 1/3 power. The discrete plaquette sums average out. As iterations approach infinity, the rigid geometric edges smooth entirely, exactly yielding the continuous metric tensor and the standard Einstein-Hilbert action. But here, the Einstein-Hilbert action is not an independent law of nature. It is the unique Banach fixed point of the network's geometric coarse-graining process. General relativity is exactly recovered by the math, but it exists strictly as the relaxed, coarse, isotropic limit of the network at equilibrium. The lattice structure also dictates the nature of gravitational attraction. The matter sector and the geometry sector of the network act as an attractor and repeller pair, pulling against each other, generating the negative sign in the equations. The universal structure theorem maps how this geometry dictates the exact coupling ratios between the physical forces, requiring 0 free parameters and 0 fitted variables. This table shows the exact structural predictions. The ratio of gravity to the weak force resolves exactly to 1/3. The ratio of gravity to the electromagnetic force resolves exactly to 13/9. To anchor these exact mathematical ratios to the absolute scale of our universe, the theory requires one single empirical calibration point, the Planck mass. Gravitational attraction and relative strength are geometric necessities of the K4 lattice structure, scaled entirely by that single mass measurement. When we examine extreme environments, like the collision of a binary black hole merger, the continuum limit of the lattice is no longer relaxed. Under massive gravitational stress, the classical metric tensor fragments. The lattice stores energy elastically. This stress forces microscopic deviations in the network. We can identify theta, representing closure angle warping, and A, representing packet spacing separation. As the structural load increases, we find C, channel slack bottlenecking, and B, branch directional biasing. The standard field equations of general relativity must be expanded to include these 4 specific delta T accommodation terms. Under strong fields, gravity stops acting like a smooth mathematical manifold and behaves exactly like an overloaded physical material, exhibiting specific failure modes. This mechanism directly addresses the cosmological constant and that 120 order of magnitude discrepancy in vacuum energy density. During the early universe phase transition, the lattice's ordering process left behind microscopic flaws, trapped framing defects. Their residual energy is the cosmological constant. Fractal recursion screens this energy, reducing it at each scale by exactly 7/192 to the nth power. This native screening scales the massive theoretical estimate down to match the observed measurements within a 7% margin of error, using 0 free parameters. The discrepancy between quantum field theory and general relativity is a direct consequence of missing this fractal screening mechanism. Unified dynamics provide highly constrained, parameter-free predictions that make the theory rigidly testable and falsifiable. The 4 microscopic accommodation channels dictate specific tidal deformability modifications and directional anisotropies that will manifest during black hole ringdowns. This diagram shows the standard general relativity ringdown waveform expected after a compact object merger. The structural yielding of the K4 lattice imprints 4 distinct signatures onto this clean signal, driven by the accommodation channels. Modern interferometers, like LIGO, are reaching the sensitivity required to isolate these high-frequency anomalies. If future observations find deviations that do not fit exactly into this branch channel defect sector family, or if the general relativity limit cannot be reached, the geometric accommodation architecture of unified dynamics is falsified.